Electricity! Electricity! Woohoo! We've got to talk about electricity! Yay! All right. I am coming to the end of this school year, and you guys have been great all along. I'm going to lecture on chapter 22, which you guys did a outline for, and I thank you for that. It's good. It's good work for you guys to work hard. Is that right? Current and circuits, right. We're going to talk about current and circuits during this lecture. There is electric current in a wire, but only if you have a completed circuit. And a completed circuit looks like this. Let's see, here's a black pen. A completed circuit is one that is a loop from a positive side of a electromagnetic force to a negative side. Okay? This is the positive side, this is the negative side. Notice the negative side is shorter than the positive side. Okay? And what happens is electrons actually move from the negative side of this, this is a electric potential, okay? A battery, car battery, 12-volt car battery, for example, okay? And you hook from the positive post down here and to the negative, which is the negative side of the battery. It's also hooked to the ground of your car. So your car is the same voltage as the negative side of this battery. Okay, and then the positive side, which is created by a chemical reaction in the battery, electrons are actually forced this direction by that chemical reaction to complete the chemical reaction inside the battery. Those electrons are transferred from one side of the battery cell to the other, and a chemical reaction is happening in the battery, and it's a reversible chemical reaction. And when you provide this battery, a 12-volt battery with 13 volts from the alternator, you make the chemical reaction go in reverse inside the chemical battery. Okay? Now, an alternator does that while your car is running with a belt. You're turning mechanical energy into electrical energy at the alternator. All right. So now, electrons are flowing in this direction. I'm going to do it like this. Show that like this. But current is described as the flow of all these electrons are moving in the wire. But current is in this direction. I'm going to exaggerate these arrows for this particular drawing. Current is the flow of positive particles. Okay? Current is often symbolized as an I, and it has the units of amperes. That's Professor Ampere came up with I. Okay? And it is the flow of positive charge. All right? I think this is a legacy thing. I think they didn't know that electrons are what were flowing in the wire once upon a time. And I think that they didn't know that electrons exist. They used to think that the atom, of course, was just a big marble with both positive and negative charges in it. They didn't know that electrons were in the electron cloud and the positive charge was at the nucleus of the atom, until Rutherford came along and shot alpha particles at gold foil. You know about Rutherford's experiment, I hope. So anyway, and then they figured out that the nucleus is very small at the center of the atom with Rutherford's experiment. And then they came along and they've learned a lot more since. Now they know that electrons are in a quantized state. They have Schrodinger's equations to describe mathematically electrons' quantized states, and it helps to explain what we observe in nature with regard to chemistry, etc. So there's a lot of evidence and observation that makes us think that our current model for the atom is indeed accurate. Okay, a lot of discussion, a lot of thought, even though we can't see them with a microscope. Okay, we're making observations about things. Okay, so they didn't know that electrons are what were flowing to make the current. They just probably assumed that it was positively charged particles moving in the wire. I mean, if you have to pick one, you got to pick one, right? I think it makes it easier to do the math in the long run, and that's why it hasn't changed. That's why they haven't changed the flow of current to be in the same direction as the flow of electrons. They haven't gone back and fixed that, because you might as well talk about the flow of positive particles, right? All right, so current. This is current in an electric circuit, symbolized by I, okay? And it's the flow of positive charge in any given circuit, but we know that electrons are negatively charged, that they are what flow in the electric current, okay? That's conventional. All right, so you have an electric circuit. There's a conservation of charge, okay? You don't destroy electrons when you have electrons flowing in a circuit, nor do you add electrons when you have electrons flowing in a circuit. You don't create or destroy electrons, you just motivate them to move, and they do. In a conductor. In an insulator, they don't move. Still a conservation of charge, though, in an insulator. All right. So now we're going to talk about an ampere. All right, Mr. Ampere, who decided we should describe current with an I. I can't remember what I stands for. You might be able to look that up, and maybe it's whatever you see when you look it up is true, maybe not. Not important. I is current, okay? And it's the flow of positive charge, but it's actually electrons that flow. All right, now let's talk about how you measure current, okay? Well, you measure current in units of amperes. I is in units of amperes. We talked about that in chapter 1 this year, all right? I is measured in amperes. And what is 1 ampere? 1 ampere is 1 coulomb of charge per second. Okay? Passing a point on the wire. Okay? So 1 ampere of charge passing in 1 second is 1 ampere. That's a lot. You know what? Let's talk about that a little bit. So how many electrons is that moving past a point on this wire? Let's talk about this point right here. Okay? The electron flux at that point is in this direction, as these curvy arrows show, the electrons, and it's all on the surface of the wire too. There's no flow of electrons at the center of the conductor. It's always on the surface of the conductor. And that's why you'll see conductors in circles, or I should say the cross-section of a conductor is often a circle, not only because it's easy to machine that way, because it draws through a die and you can change it to whatever gauge you would like. Gauge of wire is different diameters correspond to gauges, okay? And a gauge corresponds to how many dies you pulled it through. Because you can pull too hard on copper. You can try to take a copper rod down to a place that's too small in one step, and the copper will break. So gauge corresponds to how many times did you draw that copper through a die. I believe it's a 3/8 inch copper rod. you pull 3/8 inches down and make it as small as you dare, and then you pull that down as small as you dare, then you pull that down as small as you dare, and you pull that down as small as you dare, and now you got 4-gauge wire. And then you pull it down as small as you dare, pull it down as small as you, now you got 6-gauge wire. Okay? That's what that's all about. So anyway, 1 amp is 1 coulomb per second. Okay? Well, how many electrons per second equal 1 amp? All right? Well, 1 amp per second. No, 1 coulomb per second. 1 amp. Well, an amp is a coulomb per second. Right? I don't know how to spell coulomb. Let's go like that. 1 coulomb per second. Okay? That's what 1 ampere is. So ampere goes away. Now I've got coulombs per second. That's how an ampere is defined. Charge per time. Okay? And so now a coulomb. We know that there are 1 electron is how many coulombs? That's the elementary charge. 1.602 times 10 to the minus 19 coulombs. All right? So now coulombs go away. I've got electrons per second. All right? Everybody follow that logic? Actually, I probably should have said this, 1 ampere. Okay, is 1 coulomb per second. So now my amperes go away, and now my coulombs go away, and I've got electron per second. Okay? So now, did everybody see that? Is this camera pointed well? Let's make sure that's pointed well. Yeah, it is. All right, so how many electrons per second? Quite a few, actually. When you divide by 10 to the minus 19, shoo! That is amazing. So it's clear. 1 divided by 1.602 equals 0.624 equals 0.624 times 10 to the 19th, right? This is in the denominator. So I've got minus 19 here. I have positive 19 here. When I multiply all this out, all right? 10 to the minus 19. 10 to the 19th. Okay? Electrons per second. Or that is also 6.24 times 10 to the, let's see, 18th. Okay? Now, what's that? That is, I'm going to draw it over here. Oh, I'm going to draw it right here. I'll start here and move over to there. 6, 1, 2, 3. I don't know if that comma is going to be there or not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 3, 3, 3, 3, 3, 3. 62 gazillion. All right? That's a lot of electrons. I just want you to try to get your head wrapped around that for a little bit. So 1 amp flowing through this wire past this plane is that many electrons flowing. Okay? Now, it's a lot of electrons. That's why in copper, since there is at least some level of resistance in the wire, sometimes the surface area isn't enough to move those electrons without causing thermal changes. Sometimes you can feel an extension cord where you're operating, say, a hammer drill, electric hammer drill, to make a hole in concrete, and you can find where that copper wire, that undersized extension cord that you're using, gets hot, right? And now you know why. Might not even be an amp that you're pulling at 110 volts. Okay, let's keep talking about that. That's a segue into our next discussion, which is power. Okay, since amperes are charge per time, okay, and voltage is the voltage at which the charge per time is flowing, the power being used in an electric circuit in watts, joules per second. Okay, these guys were smart. These guys decided, let's define amperes as a coulomb per second. Let's define coulomb as 1.602 of our times 10 to the minus 19 of our elementary charge that was discovered by the Millikan's oil drop experiment. And then we can say this in joules and joules per second. Okay, we know that power is equal to IV. They made this true. There. Power being used in an electric circuit is equal to the current times the voltage. They made this true because they defined a coulomb the way they did. They defined an ampere the way they did, and they defined voltage the way they did, and those definitions make this true. This is in joules per second, or watt, okay, in electricity, and that's equal to the current times the voltage. All right? Everybody follow that? That's what your book says. That's what I say. There's some examples in your book about it. What do you do with that information? Rates of charge flow and energy transfer. Okay, power. What's energy that's transferred? Well, we know from talking about other forms of energy besides electricity, we know that energy is equal to power times time. Right? Remember that? So we can convert watts into joules very quickly. Okay? So this is how you deal with rates of charge flow and energy transfer. P is equal to I. They say delta V a lot. And that's true in this book, so I'll do that. Okay? So this is I'm sorry, I talked about V only, and this textbook talks about delta V. Okay? All right? All right. Diagramming circuits is talked about quite a bit here in the book, in this chapter. So we've got all these circuit symbols: a conductor, a switch, a fuse, a capacitor, resistor, potentiometer, inductor. Where's capacitor? There's a capacitor. Okay. A ground, battery, a lamp, a DC generator, a voltmeter, and the ammeter. Okay? So there are different symbols for things that you need to draw simple circuits. Okay? Now we mentioned resistance. I'm moving on to page 604. We mentioned resistance, and at the bottom of page 604, they show you different conductors and the relationship of overall resistance to the shape of the conductor the length of the conductor. Okay? They know that the area on the outside of the conductor is linearly proportional to the resistance. And that's why they know, since the cross-section changes with the surface area differently, r squared versus r. Let me think about that for a minute. I'm sorry. Yeah, r squared versus r. The surface area of a cross-section changes by r squared, but the surface area of the conductor only changes by r, not r squared, r, the surface area of the conductor. So they know that all the charge moves along the surface because it doesn't matter what the cross-sectional area is. It only matters what the surface of the conductor is in terms of overall resistance, total overall resistance measured in ohms. Now see, this guy was smart too, Mr. Ohms. He got resistance, the units of resistance named after him. And when you're talking about current measured in amperes, delta V measured in volts, and resistance measured in ohms, we know that V is equal to IR. That's another big, so here's an enormous, important formula, and we know that the change in voltage is equal to the current times the resistance, okay? So if you change the voltage in this circuit and you don't change anything else about the circuit, what will happen? The current will go up. If your voltage goes up, the current will follow. It's a linear relationship between voltage and current with a constant resistance in the thing. If you change the resistance and leave the voltage the same, your current will change linearly also, right? So they figured this out by experiment, and they determined the units of resistance to be ohms. That's this symbol right here. That's an omega, and that means ohms. So this constant, if you will, as you change delta V, so does I change, right? That slope is ohms. Okay, want me to draw a graph? I'll draw a graph right up here of voltage and resistance. Here's resistance, the changeable variable. Here's voltage, the resulting variable. No. Let me see. Yeah, not R, I'm sorry. R is the slope. Current. The measured current, how many coulombs per second are passing the spot versus voltage with a constant resistance. What you're going to find out is this. Zero voltage, zero current. As voltage increases, your current increases. Or as your current increases, I should say, your voltage increases. And this slope is equal to the resistance. Okay? Delta V is equal to IR. Okay? So this is amperes, this is volts, that's ohms. Okay? So, you can control current. These equations can be rearranged to show you what it is we're talking about. Whatever you want to find. P is equal to IV, V is equal to IR. Those are the two primary formulas that they cover so far in this chapter. Okay? I is equal to coulombs. Amperes are equal to coulombs per second. That's the definition. Okay? All right. So, if you know, there's one more equation given, but it's just the combination of these two equations right here. All right? If you plug in IR for delta V here, you get P is equal to I squared R, for example. Okay? So that's another convenient formula to remember. But if you just remember those two, you can remember this. P is equal to I squared R. That is plugging in V is equal to IR right there for delta V, so you get I squared R. Okay? It's another formula. And I, if you use this and rearrange it to I is equal to delta V divided by R, which is this is just another formula that the book mentions, I think. But I is equal to delta V over R. If you plug that in for I here, what do you get? P is equal to delta V squared over R. Okay? So they're just manipulating these two formulas right here to get these two formulas in your book. Okay? It's just a matter of rearranging and plugging in. I don't think I showed you this down here. This I is equal to delta V over R. You derive that right here. Divide both sides by R. You get I is equal to delta V over R. You plug delta V over R here for I, and you get P is equal to delta V squared over R. Okay? So there you go. Providing electrical energy. I'm looking at page 611, 612 here. Electrical transmission lines. All right. So one of the things that pops out here, a lot of times you'll see electricity energy. A unit of energy is a kilowatt hour. A lot of times you'll see a kilowatt hour unit, okay? And that's just like what it sounds like. 1,000 watts per hour times hours. Okay? Let me think if I said that right. Kilowatt hour. This is true. So it's kilowatts. It's kilowatts, and watts are in seconds, but there's hours here, times hours. So you end up with times 3,600 seconds, right? So kilowatts times 3,600 seconds is a unit of energy. This is another unit of, instead of joule, how many joules is a kilowatt hour? Let's figure that out. How many joules, I bet you can't see. I'm working over here on this side of the board. Okay? I've written how many joules equal 1 kilowatt hour? Well, 1 kilowatt is 1,000 joules per second, right? Okay, I'm going to erase these so I can continue here at this point on the board. 1,000 joules per second is 1 kilowatt, right? And now you want to change seconds to hours. So I need seconds in the numerator, because this is seconds is in the denominator. So there's 3,600 seconds per hour. Okay? Yeah, and then my hours go away. All right, and my seconds go away, and I'm left with joules. Okay? So 1,000 times 3,600. 3,600, 000. So 1 kilowatt hour is 3,600,000 joules. Okay? So when you see the units of kilowatt hour, you know it's 3,600,000 joules of energy. This is a form of energy. It's not power. okay? It's energy. That's a unit of energy, not a unit of power. Kilowatt hour, okay? If you're talking about kilowatts, that's a unit of power, isn't it? 1,000 watts, 1,000 joules per second, right? But a kilowatt times time is power. So 3,600,000 joules equal 1 kilowatt hour, okay? Something to think about, something to understand, as we all do. Because we can all do dimensional analysis. So really all that you've been taught in this whole chapter 22 is P is equal to IV, V is equal to IR, and these other formulas are derived from those two formulas, and you have to understand the units. What does it mean? What is an ampere? It's a coulomb per second. What is an ohm? Okay, it's a change in voltage per current. But you can actually measure ohms. They make those devices that measure ohms, okay, and things like that. All right, so here we go. Well, let's move on to the standardized test practice. I'll do that tomorrow. I'll give you a video on that tomorrow. If you want to try the standardized test practice without my doing it, I would almost recommend it. But this will be the end of our discussion on electricity. Tomorrow I'll do the standardized test practice. Okay? All right, you guys. I wish I could have gotten on to series and parallel circuits with you and done some lab work with you, but they took a couple weeks away from me here at the end of the year. 2 weeks. So I'm just going to have a final. I've already issued it in Google Classroom. The final is going to just be about what you learned, okay? Over the whole year, I want you to tell me 20 things that you learned over the whole year. Let me give you a few ideas. How do you write a lab report? Is it good to take a picture of your lab apparatus? Does it save you time and make your lab report look amazing compared to if you didn't have a picture in the lab report? Yeah. What about things that Mr. Kramer said that are true, right? I mean, it doesn't even have to be physics related. I want to know what you learned today or at the end of this school year over the course of this physics class. So tomorrow I'll do the standardized practice test for chapter 22, and you'll be able to get that done before the end of the semester, and or over the next week. If you give it to me next Friday, even though tomorrow's the 8th, if you give it to me next Friday, that's okay. I've been told we've got a couple weeks to finalize everybody's grades. Okay, so no sweat. If you can't get to the standardized practice test this weekend because you got something else going on, okay. All right, I love you guys, and I can't remember if I prayed at the beginning of this video, but something I was thinking on my way in today was I haven't been doing the Pledge of Allegiance. And I wonder if any of your teachers have been doing the Pledge of Allegiance. Probably some of them have thought of it. I'm going to do that now, okay? Do it with me. Stand and put your hand on your heart. Let's pray for our country. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. We pray. May it be so that there is liberty and justice for all. Knowing that we're not perfect, we're in a fallen world, but let's keep praying. I love you all, and I've been praying for you, and I hope you've enjoyed class.